Okay, guys, so just a quick announcement to begin. You would have seen this on Piazza, but I'll just relay it. So we decided to delay the homework due date by, I think it was 2 days was the announcement. And that was because we haven't covered proximal stuff until today, and so you would probably benefit from some more time to digest it. Did you have a question?
So how much is usually a bonus after work? So it's not explicitly.
Let me answer that in a second. So let me just finish the announcement. So the homework is due on Sunday night, I think, was what we said on Piazza. The proposal milestone 1, or the project proposal, which we called milestone 1, got also pushed by 2 days. And unfortunately, we cannot push back the deadline of the next homework by too much, because then that would be right against this thing we call the little test. So we're trying to give you guys some time between when the homework is done and due, and when you are going to be taking this little test to give you a bit of time to review for it. And if we kept pushing things back, then you'd be turning the homework like the night before the little test. So we're going to, for now, keep the homework 3 deadline as what it is on the website. Just try to get started early, and if we have to push it back, we'll try to think of a solution, but hopefully it'll all work out. So I'll answer the question about the bonuses. I don't really have a good answer because it just depends entirely on the problem. I guess Noyo's not listening anymore. But the bonuses are worth, usually not very much, I'll say. I think that sometimes, I think one time I wrote a longer bonus, but then I think it got cut because it was ill-phrased and maybe too hard or something. And that would have been worth more. So occasionally, if you see the bonus, and it's a longer question, that might be worth more, but I don't think that we intend to have them worth a lot. Somebody can correct me, one of the TAs, if I actually don't know what we did for the first homework. So is one of the TAs here that can correct me? Okay, well, I guess we'll have a better answer once the first homework is finished being graded, but I think it's happened right now. So I can let you know what we decided for that. Other questions?
What can we expect on the little test? Is it going to be covering mostly stuff we've already done, facts on homeworks, anything new, new novel proofs?
No, there's no proof. So the little test is take the quizzes you do after class and combine that into just more. Longer, so there's 30 questions instead of 8, but they're all true, false, multiple choice. So I think that this should be something that you don't have to really stress out for or study really hard for. It's at the level of, the quizzes, essentially. It's not trying to trick you, just trying to make sure that you understand the principles that we covered. So there's going to be no written exercises, just true, false, multiple choice. Other questions?
So you mean both the true or false after and multiple choice after?
Any other questions? Okay, today we're going to talk about proximal gradient. We've moved from gradient descent, which was 1847, I think, to subgradient method, which was the 60s, perhaps, to proximal gradient, which is much newer. So I think it's hard to pin down exactly when this came out, but some people credit it to Nesterov, among many other things. And so if that's correct, that would have been about the 80s. Although it's related to older methods, as I'll talk about today, called the proximal point method. But still, I'm saying we're getting more modern. That's the direction we're going. So last time we talked about the subgradient method, which was very general, and it was a method to minimize a convex function that we did not assume was smooth. And the method looks like gradient descent. We just replace the gradients by subgradients. So at every iteration, we compute a subgradient of our criterion function at the current iterate. And this can be arbitrary. If there are many, we can just pick one. And we're going to move in the direction of minus g by an amount tk. And these step sizes tk they're kind of preset rules, like diminishing, for example. We could take tk to be something like 1 over k. And we saw that if f was Lipschitz, then the subgradient method has a convergence rate of 1 over epsilon squared, which was notably slower than gradient descent, which was 1 over epsilon. Okay, so the upside is that it's very generic. The downside is that this can be quite slow if you're expecting high accuracy solutions. And we also saw at the end of last lecture that this was unbeatable if we're looking just generically at convex Lipschitz functions and we're only allowing ourselves to use subgradients. So there was this lower bound that was given by Nesterov that said that, you know, for any method essentially that just was a first order method in terms of subgradients, so that means that it just updated every point in terms of the span of the subgradients it's seen so far, then any such method is going to have a Lipschitz function for which it cannot optimize that function faster than this rate. So this is as good as we can expect for this problem class if we're just talking about subgradients. So that seems like kind of a depressing realization, but we're going to see today that we can restrict this problem class. So consider non-smooth functions that are kind of, in a sense, much more structured than just generically non-smooth Lipschitz functions, and see that we can recover the performance of gradient descent. And that's what proximal gradient is going to do for us. So yeah, this outline, we're going to talk about proximal gradient. We're just going to state some convergence facts about it, and you're going to prove that on the homework, I believe. You're going to prove, I think, gradient descent and also proximal gradient descent, the standard results for those two you're going to prove in the homework, and the proximal gradient result really follows quite similarly to just a generic gradient descent result. We'll talk about two special cases. This is proximal gradient applied to the LASSO, and we're going to talk about proximal gradient applied to a matrix completion problem. Both of them are kind of nice examples. And then we'll mention a bunch of special cases and acceleration. So this is a bit of a longer lecture. I expect the acceleration part to spill into next time. So we'll just see how far we get on that. But I believe we made acceleration optional on the, it's a bonus part of the homework. So you don't have to know it to do the homework. So we're going to look at functions that are decomposable in the following sense. So we're going to have a function g that's convex and differentiable, has full domain. And h is a convex function that's not necessarily differentiable. But we're going to think about h being simple and formally. Okay, so the sum g plus h is itself convex, not differentiable necessarily. But somehow we've isolated in our notation the non-differentiability to this function h, and this function h we're going to think about as being not super complicated, at least not in comparison to g. So if f were differentiable, then we would just do this for gradient descent, right? We'd compute its gradient and move in the direction of the negative gradient. And now we don't have a gradient of f, so we're going to have to do something different. And before we replace this by a subgradient, that seems natural. But we're going to look at it a little differently today, which is we're going to think about where this rule came from. And this rule came from the one intuition for it, or one interpretation was that we're going to form a quadratic around our function at a point x. So if I had some function I was thinking about optimizing, I could take a quadratic expansion around a particular point x, right? And that would be this guy right here, f of x plus the gradient of f of x transpose z minus x plus 1 over 2t times z minus x squared. So this thing is a quadratic in z. Right? That's, say, this guy. And gradient descent, remember, one motivation for it was that this update actually minimizes this quadratic. So if we were to move to this point here, that would be exactly x plus, which is x minus t grad f of x. Okay, and I'm going to call this quadratic just so we can keep track of it, f tilde sub t. So t refers to the step size and also controls the curvature of the quadratic, right? If t was very small, then this L2 term has a lot of weight. So we're going to be essentially forcing our update to be quite close to x. If t was very large, this quadratic bit has little weight. So the idea now, if we have a function of the form g plus h, where g is smooth and h is simple, is actually just to apply the quadratic approximation to g and leave h alone. Okay, so we're going to now look to move to the point that minimizes a quadratic approximation to g around the point x with curvature dictated by this t. So this is exactly just as we saw in the previous slide, but for g instead of f. And we're going to leave h alone. So minimize quadratic approximation to g plus h. And by definition, that's g of x plus grad g of x transpose z minus x plus 1 over 2t times the norm of z minus x squared. That's this part. And we're just going to add h to it. Find the point z that minimizes this approximation. Okay, and I'm just going to rearrange that into the following form. So I claim that that's the same as finding the point that minimizes the squared norm between z and the gradient update for g, x minus t times grad g. This whole squared norm is multiplied by 1 over 2t, and we add h of z to it. So to see those are the same, you can just expand this. Right, if I just were to expand this, this square, then I get a term that looks like 1 over 2t times z minus x squared. Right, I'll pull these two terms together. And then I get a term that looks like negative 2 times z minus x transpose grad g of x. Actually, the two will cancel, right, with this 1/2. And then I get a term that depends on, the norm of t times grad g squared. But since this is a minimization problem over z, I can discard that. I don't care about terms that are constant with respect to z. So these are really only the two terms I care about that involve z. And that recreates the top line, because this 1 over 2t z minus x squared is what I have here. And this thing, if I just so I must have messed up the sign somehow, because this is negative what I have. Oh, yeah, so if I just propagate the negative sign inside, right, then I get a positive. So this is exactly the linear term of the quadratic approximation, z minus x transpose grad g. Okay, so this is quite interpretable, I claim, because now we can think about there as being two terms. This first term says, let's stay close to the gradient update for g. I'm trying to minimize this over z, right? So this first term is pulling me close to what I would have done if I only had to minimize g. And I'm placing, let's say, stronger weight on that if t is smaller. And the second term is telling me that I have to remember to also make h small, right? Because I'm minimizing the sum of g plus h. So this, this function that we have here, we're going to actually define some notation for it called the proximal mapping. If you give me a function h, you pass me a point x, then we're defining the proximal map to be the minimizer of the following criterion: 1 over 2t times x minus z squared in norm plus h of z. Okay, so this thing here is just the proximal map evaluated at x minus t times grad g. Right? It's exactly what I would get from this problem if instead of having x, I had the gradient update with respect to g starting at x minus t grad g. So let's pause for a second before I move on as to why this is important, and just ask ourselves, is this actually a well-defined mapping? So as written, I think about this as a function. You pass in a value of x, it gives you back some value. For that to be well defined, we'd have to know that this problem has a unique solution. Why does this problem have a unique solution, or does it? If H is convex, let's say.
The first term is strongly convex, or the sum will also be strongly convex?
The first term is, so everything, so what you said was true, but we only need strict convexity, just to be kind of a little more precise. But yeah, this is strictly convex. Okay, so that means their sums can be strictly convex, and therefore we know it's going to have a unique solution. So this is really a well-defined map. You give me, let's say you give me an H and a T. This defines a map from Rn to Rn. So proximal gradient descent is just the algorithm that repeats these updates. So at every point x, I'm going to look at the minimizer to a problem of this form to dictate where I go next. And we can succinctly write that as x plus is just the prox of x minus t grad g. Right? That's just thanks to this notation. And in terms of, like, say, moving from iteration k minus 1 to k, it looks like this. Okay, I pick a step size tk. I look at the gradient descent step with respect to g. And I apply the proximal mapping of h to that. So one thing that some people like is that I can make this look more familiar in a form, let's say, that looks like this. X minus t times some capital G, evaluated at x itself, where g is the generalized gradient of f. So people like this form just because it looks like gradient descent. It looks like I'm moving in the direction capital G, which I'm somehow evaluating at my current iterate. And people call this the generalized gradient, okay, because it's not really a gradient. And how do you define g? You just define g exactly as you need to make this equal this. There's nothing kind of mysterious. You say you just like this form, and you have this form, because this is how we derive the update, and we define g to make these true, to make these two things the same. So I just say at a point x, capital G is x minus the prox over a step size t. So aside from maybe looking more like gradient descent, this form is actually helpful when you go to prove things about proximal gradients, because what you'll see is that this thing actually behaves a lot like a gradient. That's why it's called the generalized gradient. So in the proof of the convergence for proximal gradient in the homework, you'll do it for gradient descent, then you'll do it for proximal gradient descent, and you'll actually replace all of your grad f's by capital G's, and you'll have to use some properties of the generalized gradient that we have you develop. But it behaves like a gradient. So at this point, you might ask, why do we do this? It looks like we basically just wanted to minimize g plus h, and then we swapped it with this minimization problem at every iteration. So instead of doing minimize g plus h, I'm having you iteratively minimize quadratic plus h. Well, that quadratic is a simple quadratic. So in the variable z, it's like x minus norm of z squared, or x minus z norm squared. And okay, so in general, that may look like I didn't save much in terms of making that switch. But the key point is that for most of the functions that we care to apply proximal gradient to, this function h is quite simple, and actually this prox can be computed analytically. So for a lot of simple non-differentiable convex functions, their prox is known in closed form. And you'll derive some of those on the homework, and we'll also derive one today, or two today in class. And that makes this an efficient algorithm, essentially, when applied to g plus h, where h has a known prox. So a couple of things. Knowing the prox doesn't depend on g at all. So for example, if I told you the prox of the L1 norm, you could just as easily solve least squares plus L1 norm as you could solve logistic loss plus L1 norm, as you could solve something very complicated that was convex and smooth plus L1 norm. Because in each of those instances, the prox only depends on the choice of the non-smooth part being the L1 norm. So the smooth part g being like least squares loss or logistic loss or something very complicated but smooth and convex, it doesn't influence the updates at all as long as you can compute gradients. right? The prox doesn't depend on g. And all we need to know about g is how to compute its gradient. The convergence analysis is going to be in terms of the number of iterations of the algorithm. So every iteration evaluates the prox, and you have to just remember that that could be it could be cheap or expensive depending on h. So we tend to like to apply this to problems in which that prox is cheap. And so this iteration complexity is really reflective of what happens in practice. It's not expensive to compute the prox. But for some problems it could be quite expensive to compute the prox, and it might be misleading to say that this has a convergence rate of 1 over epsilon, because you're hiding the fact that each one of those iterations computes a very expensive prox. So let's go through an example. I think this will help solidify things, hopefully. We're going to look at I guess this is our second algorithm for the lasso. Okay, the first algorithm for the lasso was a subgradient method. You just compute the subgradient of this criterion. We saw this in the last lecture not performing very well in terms of how fast it was converging. And we know how to compute the subgradient of both the L1 norm and we know how to compute this guy's gradient, so we can perform the subgradient method. Let's now think about it through the lens of proximal gradient. Okay, and let's think about this as smooth convex function g plus non-smooth convex function h. So h is lambda times the L1 norm of beta. So the first thing to recognize is that the prox operator is actually something we already computed last time in class. This was an exercise that we did in class that exemplified using subgradients to prove optimality. Right, so this is like a lasso problem with identity design. That's another way to say it. And we computed last time in class explicitly the solution based on subgradient optimality. We took the subgradient of this and set it equal to 0 and found that the answer was to soft threshold. So we soft threshold beta by a particular amount, and that amount is lambda times t because the prox here, did I call it beta? Is 1 over 2t times, z minus beta squared, plus here it's lambda times the L1 norm of z. And that's the same as minimizing 1/2 z minus beta squared plus lambda times t times the L1 norm of z. And I can multiply through by t, won't change the solution. And we recognize this thing as being soft threshold, the input, so beta, by an amount lambda times t from last time, which is just go to every component of beta, the input, and if it's bigger than lambda, subtract lambda. If it's smaller than minus lambda, add lambda. Otherwise, set it equal to 0. That's what the soft thresholding operator does. Okay, so we're almost there. Now we have to just compute the gradient of g, right? So proximal gradient would therefore do this. It would soft threshold the usual gradient update. Right? If we repeated this over and over again, that would be proximal gradient applied to the lasso if g was the least squares criterion. And something that we see almost every lecture, or lots of lectures at least, is the gradient of least squares criterion. We can write, or the negative gradient we can write as x transpose the residuals. So this just says take beta, add a small amount t times the inner product of the features with the residuals, and then soft threshold that. So if this is large, if any of these are large in absolute value, we'll subtract off an amount lambda t from them, or if they're smaller, we'll just set them equal to 0. So now you can see directly, actually, algorithmically, it's kind of a neat feature of proximal gradient. You can directly see just from the algorithm that you're going to get a sparse solution from the lasso. Right? These steps are sparsity inducing. They're setting things to 0. So at the solution, you can see that you're going to get something that has, that has a sparsity pattern. This is often called ISTA. This is just proximal gradient applied to the lasso. It's called ISTA because people wrote a paper on this. Beck and Tabul wrote a paper on this and called it ISTA. It stands for Iterative Soft Thresholding Algorithm. It's just a very simple algorithm. So here's an example of proximal gradient versus the subgradient method for the same problem instance I showed you last time, where the subgradient method was not performing all that well. And I for each method, I gave them kind of their best choice of step sizes, try to make this a favorable situation for both of them. And we see that they have a very different convergence behavior. Right? So we might guess that, like, if this was 1 over epsilon squared, that we're back to down to something like 1 over epsilon. I mean, it might be hard to say just based on this numerically, but we're going to see that's true from a convergence result. So before we get there, we're going to talk about backtracking. So we're going to see from the theory that we can choose step sizes to be small and fixed. That has to do with the Lipschitz constant now of g, which is the smooth part of the criterion. We could also use backtracking, which is a popular thing to do in practice. And it's similar to what we do for gradient descent, but we're going to operate essentially on g and not on f. So we're going to ask for descent on g and not on f. And we're going to replace gradients by generalized gradients. Okay, so essentially, it's essentially what we had before, except for we're going to only look for descent on g, not g plus h. And we're going to be replacing the gradient of our full criterion with the generalized gradient, which is defined, remember, in terms of the prox. So that generalized gradient we define down here. It's x minus the prox of quantity x minus t grad g, divided, the whole thing divided by t. Acts like a gradient. So we choose a parameter beta that we're going to use to shrink the step sizes. We're going to try to start at some step size choice t init, and we're going to check whether the following is true. Do we progress if we were to take a proximal gradient update? Right, this is a proximal gradient update from x by an amount step size t. Do we progress less than some linear extrapolation of our g function? Okay, and I claim if you were to plug in, let's say, gt of x equal grad g, you will see this was our old backtracking criterion with alpha equals a half. Okay, we had this property that said we wanted to descend by some fraction alpha of the linear extrapolation of our function. This is just the special case with alpha equals a half. I just simplified the rule. Okay, and so this is not met, then we're going to shrink t by amount beta, like choose beta equals 0.9, and we're going to iterate until we meet. Sorry, until we get that this is less than or equal to what we see in this linear extrapolation. Question, yeah.
How do we have any guarantee that the step size given this way will result in a decrease of that?
That's a good question. So, I mean, first of all, we're using the generalized gradient, though, right? So we're using information that has to do with h. But it turns out that from our convergence analysis, this is sufficient. As long as we know that we decrease enough along the direction of the generalized gradient on g, then this is sufficient for proving the rate we need. There are variants. So I'll just say a few things. And one of the variants is that we could also ask for a descent on h as well. I just wrote down this rule because it was simpler. Another thing you might notice is that this has us recompute the prox at every inner loop of backtracking. Right, because this generalized gradient is given in terms of a prox evaluation. So if I shrink t from whatever it is to 0.9 times that value, I have to recompute the prox to get this generalized gradient. So the inner iterations of backtracking evaluate the prox themselves, and if the prox is expensive, that's not a good idea. So there are alternative formulations that require just one call to the prox. So yeah, there are several versions of backtracking essentially for proximal gradient. And this just happens to be a simple one. So let's take a look at what we know about how fast this converges. So we're going to assume similar assumptions to what we had in our gradient descent lecture on g. It's a function that's convex and differentiable. Its gradient is Lipschitz with some constant L. And h is just assumed to be convex, and we're going to kind of implicitly assume that we can evaluate its prox. If we couldn't evaluate its prox, then We couldn't perform proximal gradient as far as we defined it. So the result that you guys are going to prove in the homework is that if you fix a step size that's smaller than 1 over L, that Lipschitz constant of G, then you get the exact same result for gradient descent up to every constant that you would for proximal gradient. So at the kth iteration, f of xk minus f star is upper bounded by the squared distance between where you started and the solution divided by 2 times t times k. So this was exactly the same statement as we had for gradient descent. Okay, it's just that now every iteration, it does something a little bit more expensive typically than gradient descent in order to get that update. And the same result holds for backtracking if you replace t, this t here, by beta over L. Okay, so backtracking, this was also the same result we had for gradient descent in terms of backtracking. It gives us the same rate, and we don't have to know the Lipschitz constant. Okay, so we see that it has a convergence rate of 1 over k in this notation, or 1 over epsilon if we think about getting an epsilon suboptimal solution, which is the same as gradient descent. And I'll just repeat this for the, 4th or 5th time. I've said this many times so far. The prox cost matters. So, this is not like universally a good result. It's a good result when the prox is affordable. So let's give an example of a slightly more expensive prox, or I say like a substantially more expensive prox than the one that we saw for the LASSO. So in terms of cost, maybe let's back up. This is very cheap, right? So soft thresholding is very cheap, and it's just order p operations. So if p is the dimension of beta, then this is just order p if statements, or it's like 3 times p if statements, right? It's very cheap, or 2 if you use the absolute value instead of comparing to positive and negatives. So it's very cheap. This example is going to be substantially more expensive as the prox, but it's actually for a problem that's just computationally a lot harder, so it's still useful to use proximal gradient. So this example is called matrix completion, not something we've seen so far in this class, but actually we may have talked about this briefly in one of the earlier lectures. I think I mentioned that this was, I believe I mentioned the matrix completion in a lecture on canonical problems, and this was actually equivalent to an SDP. But in any case, we can motivate it from first principles. Suppose we have a matrix that only has partially observed entries. So we only observe some entries ij in the matrix omega, in the matrix y that are in some set omega. And this problem was really born out of the Netflix prize, where this was a matrix of, like say ratings versus people. And for any given person, you only know how they've rated a small number of movies. They're not going to have watched all the movies available on Netflix. So this, in that problem, this was like, I think it was less than 0.1% observed, or maybe 0.01% observed. So there was there were very few entries as a fraction of the matrix full dimension that were actually observed. And let's suppose we think there's some structure to how these entries are occurring. And in the case of Netflix and many other latent factor problems, it makes sense to assume a low rank structure. That actually y is close to, if y were fully observed, let's say, it would be close to a low rank matrix. And we can use that kind of modeling idea to motivate this matrix completion problem, which is to find the matrix B that's closest to y in terms of square distance on the observed entries. So this is just looking at the square distance from y to b on the entries ij in the set omega that were observed, plus lambda times the trace norm of b. And remember, the trace norm, which is sometimes also called the nuclear norm of a matrix, is the sum of its singular values. And it's a convex approximation to its rank. Okay, so if the rank was, if the rank of the matrix B was R, then it would only have R non-zero singular values. So its rank would be the sum of the indicator that sigma I is not equal to 0. Here we're actually adding the sigma i's themselves. Okay, so you can think about it as it is the analogy of the L1 penalty to the L0 penalty in the matrix land. If I had diagonal matrices, if B was a diagonal matrix, then its rank would be its L0 norm, the L0 norm of the diagonal, and its trace norm would be the L1 norm of the diagonal. Okay, so it's really like lifting those concepts up to matrices. And so by penalizing this in the problem, I'm encouraging low rankedness of the solution. Right, I want to find something that well approximates y in the observed entries, but is not too complicated. So let's apply proximal gradient to this and see what we get out. We're going to just have to deal with a little bit of notation. So I'm going to let p omega be the projection operator onto the observed set of entries. So that means if I pass in a matrix B to p omega, I get back a matrix that is equal to bij on the observed entries and is set to 0 on all the entries ij that are outside of this set omega. All right, this is the observed entries in Y. So we can take any matrix B and basically zero out entries outside of omega. So with this notation, I can write the criterion as the sum of squared entries between P of Y and P of beta. Right? Because off of omega, this is going to be 0 minus 0. And on omega, this is just going to be exactly what we see here. Right? Yij minus bij squared. So it's just a convenient way of writing that. The Frobenius norm of a matrix, right? Frobenius norm, just to remind you, is the sum of the squares of the entries of the matrix. So that's a convenient way of writing this squared term. And now we can think about this function as being my function g that's smooth and convex. So it's just a quadratic, right? So it's definitely convex, just a quadratic in B. And this thing is going to be my function h that's convex because this is a norm, right? And all norms are convex. But it's not smooth. So we're going to have to think about its proximal operator. So the two ingredients that are always needed for any proximal gradient calculation is the gradient and the prox. So the gradient of the smooth part and the prox. This one's quite easy, right? It's just going to be, I'm going to write it as negative p of y minus p of b, because we're going to be subtracting off the gradient later. That's why I just wrote this negative here. Okay, and if this is a bit confusing to you because this is written as a Frobenius norm, these are matrices, you can just go back to this and differentiate this element-wise for each ij. What's the derivative with respect to bij? You'd see it was bij minus yij if ij was in omega and it was 0 otherwise. And that as a matrix is exactly this thing. It's just p of b minus p of y, and I flip the sign for convenience later. The prox function is this guy. It's the matrix Z that minimizes the 1 over 2t times the Frobenius norm between b and z squared plus lambda times the trace norm of z. So we would have to figure this out in order to apply a proximal gradient. So here's the claim that if you give me any matrix B, the prox operator associated with the trace norm is what we call matrix soft thresholding of B at the level, this should say lambda times t. That's why the subscript's lambda times t. So how do we define this matrix soft thresholding operator? It's just given by taking the SVD of the input. So if B is the input matrix, we take U times sigma times V transpose as a singular value decomposition. So this sigma has the singular values in the diagonal. And we just subtract off lambda from every element of the diagonal of sigma and set it equal to 0 if it ever goes below 0. Right? So it just means move all of the singular values towards 0 by an amount lambda. But don't go below 0. So let's call that sigma sub lambda. And the prox of the trace norm, which is called matrix soft thresholding, is just given by U times sigma lambda times V transpose. Okay. So let me pause to see if that's even clear as a statement. Okay, the proof is sketched here in the notes. On a previous iteration of the course, we had you guys prove this in the homework, and this was always one that people found difficult, so you guys lucked out this year because it's not in the homework. But it's a challenging example of deriving a prox. It's substantially more difficult than deriving the prox of the L1 norm. But I'll just highlight how we do it, because in doing so, I'm going to remind you that the way that you would, in general, evaluate a prox function is to use subgradient optimality. Right? So I want you to minimize, in this case, overall matrices Z, 1 over 2t times b minus z for Venus norm squared, plus lambda times the trace norm of Z. So if this was something else, some function h, then how would you do this? Well, the only tool we know how to do this at this point to solve this is to use subgradient optimality. This is not smooth, right? Because this part is assumed not to be smooth whenever we're doing proximal gradient descent. So we have to take a subgradient with respect to z, set it equal to 0, figure out when we can satisfy that, and that will be the solution because it has a unique solution. So that's, in fact, what we did when this was the L1 norm, and it's what we're going to do here when it's the trace norm. And I'm just going to skip a difficult part, which was just computing the subgradient of this part. That's the most challenging part. So that notwithstanding, we can just take a subgradient and set it equal to 0. I think I'm going to move the t up. Yeah, I'll just make this equivalent to minimizing 1/2 b minus c for Venus norm squared plus lambda times t times the trace norm of z. And okay, so now I just have to take a subgradient and set it equal to 0. Right? The first part is differentiable, so it becomes b, let's say it becomes z minus b plus lambda t times, what did I call it in the notes? I didn't call it anything in the notes. I'll just call it gamma here. Some matrix gamma. This must be equal to 0. This is what subgradient optimality would say. For some gamma, matrix gamma, that's in the subgradient of the trace norm, let's say capital X, evaluated at x equals z. Okay, so as long as I can find gamma in the subgradient of the trace norm evaluated at this matrix Z that satisfies this, then I have the solution, because this has a unique solution by strict convexity. So this is the most challenging part, and I'll just state this fact. And this is something that if you're curious to know how to prove, you can look back at, well, I'm not sure on previous homeworks how structured it would have been in terms of hints, but you can come to my office hours if you're curious to know how to prove this. But this is a fact. Suppose I give you a matrix X, and suppose X is a singular value composition U sigma V transpose, then the trace norm is the set of all matrices that are of the form UV transpose plus W. Okay, where W is a matrix that has operator norm less than or equal to 1. This means the largest singular value of W is at most 1. And it's orthogonal to the columns of U. And it's orthogonal to the rows of V. Okay, so that is the subdifferential of the trace norm. In fact, one direction, actually just proving that these are all subgradients is not difficult. If you just plug this into the definition of a subgradient, then that side is not difficult. Proving that these are all the subgradients, So this is truly the subdifferential is the difficult part of this fact. But it's useful because you might see the trace norm pop up in a lot of places, especially if you're interested in low rank estimation or estimation with low rank regularization. So knowing this fact is going to be useful. Okay, so now I claim that we can just plug in gamma to be equal to st of z, and it's going to be a subgradient, and b it's going to satisfy this equation. So let's first prove that it satisfies this equation. So we need to know that b, so checking this equation, says that b should be equal to z plus I'm sorry, this is completely confusing and incorrect. We need to plug in b equals soft threshold aversion of z, right, and check that it can be made equal to z plus lambda t times gamma for some gamma that's a subgradient. Okay, so this is the check we need to complete. Okay, so let's use the singular value decomposition of z. Let's assume that it's of this form. Okay, and if we look at as an example, if we look at z minus the soft threshold aversion of z, we have to say that it's equal to lambda times t times say negative gamma, where gamma is a subgradient of the trace norm of evaluated at this particular value. So just using the SVD, right? This thing can be written as u times sigma minus sigma sub lambda times v transpose. Okay, and we want to check that this is equal to lambda times t times minus gamma. Or in other words, for some gamma that's a subgradient, we want to check that gamma, which is equal to u times sigma sub lambda minus sigma divided by lambda times t times v transpose. We want to check that this is a subgradient. Okay, this should say sub t. Everywhere where I have sigma sub lambda, it should be sigma sub lambda times t. Okay, so at this point, actually, we're essentially finished. If we, at least if we know that the subgradients are of this form I wrote up here. Because if we look at this matrix here, okay, let's suppose that I order the singular values in decreasing order. Then remember, this thing is going to be either equal to this minus lambda times t, or 0, depending on whether or not the singular value is bigger than lambda times t. So in the case when it's in case when it's larger, right, I'm just going to get a bunch of negative 1s. That should be 1s. Somehow I missed a sign somewhere here.
Based on what you had on the lections, you said E equals the software.
That would completely explain everything. So here we're trying to find the value of z that for a given b minimizes this criterion, the Prox criterion. So yeah, so of course we have to say that the minimizing, thank you for catching that, the minimizing z, which is the optimization variable here, is a soft threshold of b. So if we propagate that through, then we're going to see that the signs get flipped. That's the difference, is that the signs are going to get flipped when I make this comparison. So let me just summarize this by saying, sorry guys, that was messy. I'll just summarize this by saying the subgradient optimality with this choice it's going to become, it should become proving that this is indeed a subgradient. It's the same steps that I took, but with b and with the roles of b and z reversed. So if we can prove this is indeed a subgradient, then by construction it's going to satisfy the subgradient optimality condition up here. And if it's a subgradient, then we've just computed the prox. And the point was that this matrix inside here, when the singular value is larger than lambda times t, it's going to just be 1. So this is a diagonal matrix by construction, and it's just going to be 1 for all the singular values that are larger than lambda times t. Because it'll be something like sigma minus the quantity sigma minus lambda times t. That's what I'm subtracting off. The sigmas cancel, and I just get lambda t over lambda t. So it's what's the difference between sigma and sigma minus lambda t? It's just exactly lambda t, which is what we're dividing by. And when it's smaller, it's going to be something else. And the purpose of writing it this way is that you can see that I can actually break off u and v transpose with the identity in between and consider the remainder term as w. And this remainder term that I construct from here, so this has to be a subgradient of the trace norm of, let's say, x, evaluated at x equals the soft thresholded version of b. And that's only going to have factors u and v transpose that survive the singular value thresholding. So I can write this exactly as, let's say the top however many k, u times v 1 through k transpose plus w, where this w comes from multiplying this out and taking these bottom right entries. And you'll see that by construction, this is of this form, where this w is actually orthogonal to these u's, and it's going to be orthogonal to these v's as well, just from the fact that the singular factors are orthogonal. Okay, so I botched that. It was a bit of a messy proof. The recap is that we do this generally by taking a subgradient of our criterion, setting it equal to 0. And in this particular case, the challenge was actually in computing the subdifferential of our non-smooth part, which I did for you on the slides. The part that was not supposed to be challenging, that I managed to make challenging, was actually plugging that in and showing that we could set it equal to 0. I just reversed the roles of the optimization argument and the input to the prox for no reason other than I was being silly. But in general, once you've computed subgradients, it should be fairly straightforward to figure out what the solution is by setting the subgradient equal to 0. Okay, and in this case, it was just a complicated subdifferential. But this should be something that hopefully you guys can use as a fact from now on. Just the prox of the trace norm is matrix soft thresholding. So let me just get to the conclusion of this matrix completion example, and then we'll take a quick break. So the conclusion is the following. So now we know how to take a proximal gradient step, which is we take a gradient step. Remember, the gradient was negative py minus p of b. So here I'm moving in the direction of negative of that, which cancels the leading negative, times t. So this is the gradient step if all I had was the smooth part. And when I get that matrix back, I'm going to soft threshold it, which means I'm going to have to compute its SVD. And then I'm going to have to set the singular values that were smaller than the amount lambda t to 0. And the ones that were bigger than lambda t, I'm just going to shrink. That's going to be my new update called b+. So in this particular instance, the gradient is actually Lipschitz with a Lipschitz constant of 1. Right? If you can see that by just looking at, if I looked at the difference between, let's say, this at b and this at b prime, it's just going to be p of b minus p of b prime. That's the difference in the gradients at b and b prime. And p of b can only kill entries, right, or leave them untouched. So that's not going to affect the Lipschitz constant. And the Lipschitz constant you can see is just exactly 1. This comes from writing out the definition of what Lipschitz continuity means. And by our theory, we know we can now take a step size of 1 over L, which is 1. So I'm going to plug in 1 here for the step size. I know it converges from the theorem. And I get p of y plus b minus p omega of b, which I'm calling p omega perp. So this projects onto the unobserved set. It does exactly the opposite of p. It actually kills all of the entries of the matrix that are in omega, and it leaves the one that are in omega complement untouched. Okay, it's the analogous projection operator, but for omega complement. And that's my update. So it's actually a very simple algorithm, and I think it's quite intuitive. At every step, just take the observed entries of y, fill in all the unobserved entries with what you thought the unobserved entries should have been in the last iteration. Right? This bij I'm only imputing in the entries omega complement. Then take that matrix and reduce its rank. It's a form of regularization, right? I'm going to be reducing its rank by doing this matrix soft thresholding. So I take the SVD of this, and then I send the small singular values to 0, and I shrink the others, and that becomes b+. So that's called soft impute. Like ISTA, it was proposed, it was an application of proximal gradient to a particular problem, and it was at its time one of the more efficient algorithms for matrix completion at large scale. So this is generally expensive to do in SVD, but this is a case in which I have a sparse plus low rank matrix. So B is low rank by construction. Every iteration it's being kept to be low rank. This is sparse by assumption. I'm doing matrix completion, so I'm missing a lot of entries. So that means I'm actually sending a lot of these to 0. And it turns out to be a particularly efficient special case to compute SVDs of sparse plus low rank matrices. And that itself requires a lot of work, but let's just say there are good numerical linear algebra routines for doing so. So in this case, this SVD can be done more efficiently than in a typical case, which makes this prox okay. Okay, so we're a little bit late, but let's still take a break, and we'll come back and finish off what we can. Okay, guys, let's jump back into it. So we have just a little bit more to cover, and we'll see how much we get in terms of acceleration today. So some people also call proximal gradient composite gradient descent. In fact, I think that was maybe the original name for it. So you can read about Nesterov's papers on composite gradient. That'll be what it's called. It also was for a time called generalized gradient descent. And that name, I think, it's an interesting name, and it's worth kind of clarifying why it's called generalized gradient descent. And it's because we can get several special cases out of proximal gradient. And so what we've done so far, which is we've told you what it is, told you how to do backtracking, we've told you when it converges in terms of step size choices and how fast it converges. That actually implies all those results for a bunch of important special cases. And here are the special cases. If I take HB to be 0, then we get back gradient descent. So that should hopefully be already intuitively obvious to you without going into too much more details. But I think the next slide... Okay, the next slide actually do not go into that. So let's just make sure that is an intuitively obvious fact. So if h is 0, what's the prox? What is the prox when h is 0? What do you guys think? So h is 0. So it's just the identity, right? Just gives me back x itself. So it doesn't matter what t is. So if I do, if I do x plus, which is the prox of x minus t grad g, in the case when h is 0, I just get this thing. It's the identity operator, right? So I get back whatever I pass in, which is the gradient update. And if h is 0, this is the criterion, so g is the criterion, so I'm doing gradient descent. Okay, so that's a special case. So everything we've talked about and proved so far, in fact, kind of is strictly more general than what we did for gradient descent. How about when h is an indicator function? So it's 0 when its argument's in a set C and it's infinity otherwise. We get projected gradient descent, which I'll talk about in the next slide, and is a very natural algorithm itself. And when g is 0, when the smooth part is 0, we actually get something called the proximal point algorithm or proximal minimization algorithm. This is an older algorithm than proximal gradient itself. I think this goes back to Rockefeller, but I think it's kind of a weird special case. You have a non-smooth function that you're minimizing, and it's prox. And I don't know of a lot of cases I don't know that actually has a lot of interesting special cases, but it is an algorithm. So what we know is that all of these algorithms have 1 over epsilon convergence rate, for example. And let's first go through projected gradient. So remember, minimizing some function over a closed convex set C is equivalent to minimizing that function plus the indicator. Right? This thing being 0 on the set C and infinity off the set C. So if I ask for the prox function of the indicator, okay, it's equivalent to minimizing this quadratic only over the set C for the same reason. And at this point, t doesn't matter. Right? The 1 over 2t doesn't matter. And this is exactly the projection operator onto the set C. So the prox in the case of an indicator just projects onto the set C. So another way to think of the prox, so just like I said, you can think about the generalized gradient is more general than the gradient. Another way to intuit the prox is to think about it as being more general than a projection. So a special case of the prox is a projection. Okay, and that's when you take the h function to be an indicator. If h is not an indicator, but it's just a generic convex function, then the prox is like a special kind of h projection. And in fact, it retains a lot of properties of projections. So one important property that it retains is non-expansiveness. If you ever project, let's say, a point x onto a set C and a point y into a set C, then the distance between the projected points is no farther than the distance between the original points. if that set was convex. Right? That should kind of be intuitively reasonable to you. If I were to project x and y, that the projected points only get closer, they can't get farther after projection. That's also true of proxes, actually, in general. So if I take the prox of x and the prox of y, then the difference between the proxies is the distance is no bigger than the distance between x and y for any function h. So it retains that property and other properties of projections. It's just a more general notion. So, okay, we just saw that when we take the indicator function as our function h, we get projections out of the prox, and therefore the update in proximal gradient is just this. Take a gradient update with respect to g and project onto some set c. This is just projected gradient. And we get convergence now for free. There's no new convergence analysis needed. We know this converges. We know it converges with the step size choices and with backtracking as we've defined it. And it converges at the rate 1 over epsilon. All right, so here's just an example of projected gradient. I'm moving in the direction of the negative gradient. Let's say these are the contours of g is what I'm showing you with these contours. And this is, say, my constraint set, C. This takes me in the direction of the negative gradient. And then I have to project back onto C to get my next update. That's projected gradient. Okay, a special case that I don't want to spend as much time on because I think it's really not as widely used is proximal minimization algorithm. It's just a special case when g is 0. So when g is 0, the gradient's 0, right? So the update is just x plus equals prox of x. And that's a very simple algorithm. If we could compute that, then that's an algorithm that we could use to minimize any convex function h. And it would be faster than the subgradient method, right? It would be converging at the rate 1 over epsilon, not 1 over epsilon squared. So it sounds really great, but it's not typical that we kind of are in a situation where the entire criterion is something whose prox we know. So it's really not used very much. Okay, what happens if we can't evaluate the prox? So of course, people are going to try to use this when, let's say, this is not known in closed form. And it's interesting to ask what happens if you were to try to apply another optimization algorithm in this inner step to try to approximate the prox. And this is an easier problem, let's say, than the original one, right? So the smooth part here is very simple quadratic. So you might apply something to this. We'll learn many more techniques as you go through the course. You might apply one of those techniques to approximate this. And then you could ask, what happens if I plug that in and try to do proximal gradient? So in general, it's not clear if we just get an approximation kind of arbitrary nature. But if you know that the errors in approximating the prox, so if you have some, let's say you have some prox tilde, and I look at the difference between this approximation to the prox and the actual prox as I go on in iterations of the algorithm. I guess I should use an x here. If this gets smaller, if these errors get smaller, call this ek at some rate. So if I actually force myself to maybe make better and better approximations as the algorithm carries on, then you can get the original convergence rates out of proximal gradient. So the kind of rough rule of thumb in practice is that it doesn't matter so much at the early iterations how well you're approximating the prox, but closer to convergence, you have to start asking for higher accuracy approximations. And there's a nice paper that shows that under some conditions on how fast these are diminishing, these errors, you get back all of the kind of theory for proximal gradient. Okay. So I think we have only, looks like a little over 5 minutes. I'm just going to tell you what acceleration is, and then next time we will spend a little bit more time discussing it. So there's a interesting history behind acceleration, and all involves Nesterov. It turns out that we can accelerate proximal gradient, which we know means we can accelerate gradient descent as well, in order to achieve a faster rate than what we already saw, which is 1 over epsilon. We can actually get it to work at a rate 1 over the square root of epsilon. And there were 4 kind of landmark papers written by Nesterov, starting in 1983 and ending in 2007, which explained how to do this for both smooth functions and then also the case where you have composite loss, like G plus H. And they're not actually the same. There are different ways to do acceleration. So there are still different ways to perform acceleration. And just for the purposes of simplicity, I just picked one, which I thought was the simplest, which is an extension of his original 1983 acceleration idea for smooth functions to the case where you have a composite loss, G plus H. And there's a nice paper that was written by Beck and Taboul that it kind of gives this extension. So here's the method. So I think we'll only have time just to define the method and possibly state the convergence result, and then we'll probably have to quit. So we're going to have the same setting as before, G plus H. G is convex and smooth, H is convex. And we're going to be looking at an algorithm called accelerated proximal gradient descent, which is given by choosing some initial point x0 and then performing what looks like essentially a momentum update. Okay, so I'll explain this in a second, but think about this as you're at the point xk minus 1, and usually you would just evaluate the gradient of g at xk minus 1, move in xk minus 1 minus the gradient direction, and apply the prox to that. What this is doing instead is that actually it's having you move from xk minus 1 to a new point v, and you can think about that as that you're being pushed towards v due to momentum from previous iterations. So you're actually using past information to push you towards a new point v. Then you're making a gradient update in a proximal application starting at v. Okay, so if I just replaced, if I just took v equals xk minus 1 and ignored this term, that would be proximal gradient. Okay, but instead I'm actually looking at the vector that points from xk minus 2 to xk minus 1, looking at this vector. And while I'm at xk minus 1, I'm going to add, okay, some small amount of this vector to get to a new point v. And at this point v, I'm going to be evaluating the gradient, moving the direction of the gradient of g and applying the prox. So if let's suppose I've been traveling in some direction, this is going to be pushing me to continue on traveling in that direction, trying to get me to take a gradient step at a point v that's experienced some momentum. What are these momentum weights? That's going to control how far we get pushed from x to v. Right, that's these weights right here. Well, they start off being 0 actually, because at the first step we define, let's say we define a point, starting point x0, and we define another point x minus 1 as for notational convenience. So this difference is 0, and there's no momentum at the first iteration. K equals 1. At k equals 2, there's also no momentum, right, because this is 0. And then we start seeing greater and greater momentum, right? This starts approaching 1 as the iterations carry on, when k gets large. Okay, and the intuition being that as we get closer to optimality, the gradient of g is, well, actually, let's say as I get close, let's just say that the generalized gradient as I get closer to optimality is going to get smaller and smaller. So effectively, my updates are going to be smaller and smaller. I want more and more momentum in those cases because I want to actually continue to make progress in terms of optimization. I don't want to slow down just because the gradient's getting small. That's why the momentum is getting larger. And if you take h to be equal to 0, then you get accelerated gradient method. So this prox goes away, all right? And then it's just taking gradient descent and adding momentum before you do the gradient update. Okay, here's a picture of those momentum weights. So just to show you how close they get to 1, you know, I'm just plotting k minus 2 over k plus 1 as a function of iteration k. So this is just an example. I showed you already, this was proximal gradient for the LASSO, right, which you saw was just iterative soft thresholding. This was subgradient method for the LASSO, which was just taking subgradients and moving in the direction of the negative subgradients. This is accelerated proximal gradient. So it's much, much faster. This is the difference between 1 over epsilon squared, 1 over epsilon, and 1 over the square root of epsilon. It's a much faster convergence rate. If you were to zoom in, which I think I got rid of that plot, you'll notice something, which I'll mention, and then we'll call it a day and resume on Wednesday. You'll notice that the blue criterion here, it does this. So it actually is not a descent method. It has these ripples that people kind of fondly call Nesterov ripples. That's what they're called. So it's not a descent method, not like gradient descent. It actually can increase the criterion, but it has a much faster convergence rate. Okay, we'll just pick up from where we left off next time. Yeah.